Hello and welcome back to Retured. I'm Amy. In our last video in Basics of AI series, we explored mean-squared error, which is perfect for an AI learning to predict continuous values, like the price of a house. But what happens when the AI needs to make a choice, a yes or no decision? For that, we need a different kind of guide, a different language for learning. Today, we're diving into that language, binary cross-entropy. It sounds complex, but the core idea is wonderfully simple. Binary means two parts. In our case, two possible outcomes. Think spam or not spam, cat or not a cat. And cross-entropy? It's a concept from information theory that, in the world of AI, measures the surprise of the model when it gets something wrong. Let's use an analogy. Imagine you are an AI and your job is to predict if it will rain tomorrow. You don't just say yes or no. You give a probability. Let's say you predict an 80% chance of rain. The next day, you look outside, and it's pouring. You were right, the outcome matched your high confidence. There's very little surprise here, so the penalty or loss should be very small. But what if you predicted an 80% chance of rain, and the next day it's bright and sunny? You weren't just wrong. You were confidently wrong. That's a huge surprise. Binary cross-entropy is designed to give a very large penalty for this kind of confident mistake. It teaches the model that being overconfident and wrong is much worse than being uncertain and wrong. Now for the flip side. If you predict a 10% chance of rain and it's sunny, you were right again. Low surprise, low penalty. But now, consider this. What if you predict only a 10% chance of rain, but it pours? This is the biggest surprise of all. An event you considered almost impossible actually happened. Binary cross-entropy gives this scenario the highest penalty. It's the model's way of saying, wow, I was completely blind to that possibility. I need to learn from this immediately. This idea of surprise is captured mathematically using logarithms. We don't need to get lost in the math, but here's the key intuition. The loss function has two parts. One part calculates the loss if the true answer is 1 or yes, and the other part calculates it if the answer is 0 or no. Depending on the actual outcome, only one part of the formula is activated. So when it actually rains y equals 1, we look at how close the model's prediction was to 1. The closer it was, the smaller the log of p term, and the smaller the penalty. When it's sunny, y equals 0, we look at how close the prediction was to 0. It's an elegant way to punish a model based on both its answer and its confidence. Let's make this concrete with some Python code. Imagine a model has made 3 predictions about whether an email is spam or not. A probability close to 1 means definitely spam. We have the predictions and the actual labels, 1 for spam, 0 for not spam. Using NumPy, we can implement the binary cross-entropy formula directly. We calculate the part for the spam cases and the part for the not spam cases, add them up, and find the average. This single number, the final loss, tells us how well the model is doing across all its predictions. So, where does this powerful tool show up in the world of AI? It's everywhere. It is the default loss function for any binary classification task. Training an AI to detect fraudulent credit card transactions? That's BCE. Diagnosing a medical image as cancerous or benign? That's BCE. Analyzing the sentiment of a movie review as positive or negative? You guessed it, BCE. Now let's talk about the cutting edge, generative AI. Remember GANs, or generative adversarial networks? They have 2 parts, a generator that creates fake images and a discriminator that tries to tell the fake images from real ones. What is the discriminator's job? It's a binary classification problem. Is this image real or fake? And the engine used to train that discriminator is binary cross-entropy. And what about large language models? While the core training of an LLM involves predicting the next word from many possibilities, a task for categorical cross-entropy, we often fine-tune these models for specific jobs. If we fine-tune an LLM to be a toxicity detector, its job is simple. Is this comment toxic or not toxic? That's a binary choice, and we use BCE to make the LLM great at it. So a common question is, why not just use mean-squared error for these probability tasks? You could, but it's like using a screwdriver to hammer a nail. It doesn't work as well. BCE is designed for probabilities. It creates a much stronger signal for the model to learn from, especially when it's confidently wrong, pushing it to get better much faster. So to recap, binary cross-entropy is the perfect loss function for any yes or no prediction. It works by measuring the model's surprise, heavily penalizing it when it's confident and wrong. This simple but powerful idea is what enables AI to master classification tasks all around us. Pause for a moment and think about your favorite apps. Where might binary cross-entropy be working silently in the background? Is it deciding what content to recommend to you? Is it filtering your emails? Let me know your ideas in the comments. Thank you for joining me on this journey into the heart of AI decision-making. If you enjoyed this explanation and want to keep learning with us, be sure to like this video and subscribe to Retured. I'm Amy, and I'll see you in the next one.